Hello everyone. Today we are going to analyze this propped cantilever beam. In this beam there is uniformly distributed load 24 kN per meter. It starts at a distance of 3 meter and acts for a distance of 3 meter. The span of the beam is given as 8 meter. We know that this analysis is a little difficult because we are having the uniformly distributed load in between the beam. To make the problem easy, we can extend the uniformly distributed load from the point C and up to the point A. You can see that I have extended the uniformly distributed load from the point C and up to the point A. This load is acting downwards, so from the point C and up to the point A, we have to apply uniformly distributed load of same magnitude in the upward direction, so there will be no change in the answers. We know that the upward deflection due to RB will be equal to the downward deflection due to the uniformly distributed load. In this case, we can use this expression. This is the deflection due to RB. This is the deflection due to the uniformly distributed load which is acting downwards. This is the deflection due to the uniformly distributed load which is acting upwards. Since it is acting upwards, it should be denoted as negative. EA is common, we can eliminate. Finally, we will get this expression. Now from the point B and about the point A, we are going to find the bending moment values and draw the bending moment diagrams. In this case, we have to follow left hand side rule. Clockwise will be negative and anti-clockwise will be positive. RB is acting in the anti-clockwise direction, so that it will be positive and the distance is 8. 8 into RB, it will be 8RB. The uniformly distributed load 24, which is acting downwards, is acting in the clockwise direction, so that it will be negative. We know that with the uniformly distributed load, we have to multiply the distance and the distance by 2. Here the distance is 6, so 6 into 6 by 2. When we calculate this, we will get minus 432. Now let us take the uniformly distributed load 24, which is acting upwards. It is acting in the anti-clockwise direction, so that it will be positive, and the distance is 3. So 3 into 3 by 2. When we calculate this, we will get 108. We know that the bending moment diagram due to RB will be in the shape of a triangle. The diagrams due to the uniformly distributed loads will be in the shape of parabola. Now let us find area 1 x1 bar. We know that it is a triangle. We know the area formula of a triangle, half into BH. Here the breadth is 8 and the height is 8RB. So this is the area. Now let us find the x1 bar. We have to find the centroid distance about the right side. The formula is 2 upon 3 into B. Here the breadth is 8. So it is 2 upon 3 into 8. For area 1 x1 bar, we will get 512 upon 3 RB. Now let us find area 2 x2 bar. This is a second degree parabola. The area formula is 1 by 3 into BH. Here the breadth is 6 and the height is 432. So this is the area. Let us find x bar 2. The centroid distance about the right is 3 upon 4 into B. But we have to add the remaining distance also, that is 2. So 3 upon 4 into 6 plus 2. Now let us find area 3 x bar 3. We know that this is also a second degree parabola. So we have to use the same area formula, 1 upon 3 into BH. Here the breadth is 3 and the height is 108. This is the area. The centroid distance about the right is 3 upon 4 into B. Here the breadth is 3. So 3 upon 4 into 3. Then we have to add the remaining distance, which is 5. For area 2 x bar 2, we will get 5616, and for area 3 x bar 3, we will get 783. In this expression, we have found everything. Let us apply them. Finally, for RB, we will get 28.32 kilonewton. Now let us apply the rule sigma V is equal to 0 and find RA. Now from the point B, let us take a moment about A and find MA. RB is acting in the anticlockwise direction, so that it will be positive, and the distance is 8. The uniformly distributed load 24 is acting in the clockwise direction, so that it will be negative, and the distance is 3. Then we have to open a bracket. We have to divide the distance 3 by 2. Then we have to add the remaining distance, which is 3. Let us assume that MA is acting in the anticlockwise direction, so that it will be positive. Finally, for MA, we will get a positive value. That means our assumption is correct. MA is acting in the anticlockwise direction. Now, using the right hand side rule, we can find the shear force values. Here you can see the shear force diagram. In this point, the shear force becomes 0. In this point, there will be maximum positive bending moment. Let us make a section in this point and find the distance. You can see that I have made a section at a distance of x from the point D. Using the left hand side rule, we can make the expression for the shear force, which is 0. For x, we will get 1.18. Now let us find the maximum positive bending moment. RB is acting in the anticlockwise direction, so that it will be positive, and the distance is 2 plus 1.18, so it will be 3.18. The UDL is acting in the clockwise direction, so that it will be negative. With the UDL, we have to multiply the distance and then the distance by 2. For the maximum positive bending moment, we will get 73.34. Now let us find the bending moment in the point D. RB is acting in the anticlockwise direction, so that it will be positive, and the distance is 2. Finally, we will get 56.64. To find the bending moments in the points A and C, we can use the right hand side rule because it will be easy. Let us find the bending moment in the point A. In the point A, we have MA, which is acting in the anticlockwise direction, so that it will be negative. Now let us find the bending moment at C. In addition to MA, we have RA. RA is acting in the clockwise direction, so that it will be positive, and the distance is 3. For the bending moment at C, we will get 33.6. Here you can see the bending moment diagram. In this point, the bending moment becomes 0. This is the point of contraflexure. We can make a section in this point in the beam and find the distance. You can see that in that point, I have made a section at a distance of x from the point A. We know that in this section, the bending moment is 0. Using that concept, we can find x. Let us apply that.